All right, the practice final, question number 3. Part A, the Fourier transform x of j omega of the continuous time signal x of t is shown below. What is x of t? So what we have here is let's just pick it apart. We have an amplitude of 1. It goes out to, and that is its amplitude. So x of j, let's just define it like this. And it's equal to 1 when negative pi over 2 is less than, or when omega is greater than negative pi over 2, but also less than pi over 2. And then it's equal to 0 for the rest of time. Now, if you look at table 4.2, where is it? It's 2/3 of the way down or so. We have the signal sine of capital W of t over pi t. That has a ft that looks like x, or on the sheet it has x of j omega equal to 1 when omega is less than capital W. The magnitude of omega is less than capital W, and 0 when the magnitude of omega is greater than capital W. Magnitude or absolute value, whatever you want to call it. And we can see that this perfectly fits what we have going on here. So that tells us that capital W is equal to pi over 2. So the continuous time signal, part A, x of t, is going to be equal to the sinc function sine of pi over 2 times t over pi t. So that's part A. Now, part B. Sketch the Fourier transform P of j omega. So P of j omega is equal to the Fourier transform of cosine of pi t over 2. Cosine of pi t over 2, this has an omega naught equal to pi over 2. So we could just write cosine of omega naught t. And the Fourier transform of a cosine function is pi times a delta omega minus omega naught. In this case, this is pi over 2 plus delta of omega minus or plus pi over 2. And what this is saying is, so we have cosine right here. We have this cosine, right? We have cosine of pi t over 2. And what we're using the Fourier transform to do is we're trying to have the Fourier transform tell us, well, what's the frequency content of this signal, right? Because you plot this in the time domain, you get some sinusoid or whatever, right? And that sinusoid has a frequency. If it was superimposed sinusoids, then there could be a bunch of different frequencies, but we have just a single sinusoid here. And what the Fourier transform is trying to do is tell us, well, what is the frequency content of this signal? And we can see here that we're going to get, if we make a plot and we have the magnitude of P of j omega right here, and we have this independent axis as omega, then if this is negative pi over 2 and this is pi over 2, we get an impulse right here and right here with a magnitude of pi. So what this plot is showing is it's just telling us what the frequency content of cosine of pi times t over 2 is. And it makes sense that this is our only frequency content because we have a single sinusoid. So that's what the Fourier transform is trying to do, is tell us what's going on in the spectrum of our signal. And then whenever you hear the word spectrum, you want to think frequency domain, not time domain. More specifically, Fourier domain, because when you get into the S domain, you start talking about transients and whatnot. So, but that's part B. Now, for part C, sketch the Fourier transform of y of j omega, where so we have part C, we have y of j omega is equal to the Fourier transform of x of t times p of t, which that's equal to the convolution of x of j omega and p of j omega. Now, we have that scaling factor we have to deal with here. It's on the formula sheet, so it's going to be 1 over 2 pi, and it's going to go from negative infinity to infinity, and x of j theta, where theta is just like our dummy variable, just like tau was in the time domain, omega minus theta. I missed a j. There's a j right here, but whatever, not a big deal. And that's all doing the integration with respect to theta. But if we just think about this, if we think about this signal, well, we flip it in. So we have a box right here. We have, let me draw some box. Actually, 1 second. We have a box that comes up and it's like this. So red is x of j omega. Now, when I'm doing the convolution, right, I would flip this box, which I don't need to flip it because it's symmetric, but I flip it and then I just pass it through here. So as I pass it through, it's just going to trace out the area. So it's coming in, 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 boom, 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 boom. So you can see right here that when the result from convolving the box and the left impulse is going to be a box that is a length of pi, right? Because we have pi over 2 right here, and then we're going to have a pi over 2 over here. So if I drew, here's y of j omega. I guess we don't need the magnitude because it's all positive anyway, so let's just leave it as that, and this is omega. So here's negative pi over 2, and here is pi over 2. Well, we have pi times a box of an amplitude of 1, and we have the scaling factor here, right? So we have pi times 1, which is pi, times 1 over 2 pi, which gives us 1 over 2. So we're going to get the first, gives us this, and this would be out here, this would be negative pi, and here we are 0, of course, and this is an amplitude of 1/2. Let me get a little more space over here. Now, I keep going with this box, right? And as soon, at the same moment that I am done with my left hand impulse, I am hitting my right hand impulse, and it's going to give me the same amplitude. So I keep coming, and you can see here that I go through, and this box is going to have the same pi over 2 to the left and same pi over 2 to the right. The convolution of the box with the right hand impulse. So that's going to give me a, if I do a pi out here, and let me get rid of the bottom leg there. Dang it. Well, here's my box that's convolved from the left impulse, and then I'm just going to keep that box going until I get over here. And that's what the Fourier transform y of j omega is going to look like. You could go through and do the multiplication. I don't think it'd be all that fun. Or you could just remember what convolution is. And when you have simple signals like this, a simple box with some simple impulses, you should by now know how to convolve that graphically. And if you don't, there's a couple convolution videos up here I posted prior that would be helpful to watch. But that, let me just that should be, I guess the yeah, well, you really wouldn't have to do it either like that. You could just, because we have the delta functions, I guess. Yeah, if you have the delta functions, um, if you have the delta, so let's do this. Let's actually do the analysis of it. So we have 1 over 2 pi, and this is nothing more than a convolution. So it's uh, x of j omega involved with, and we can write out these delta functions. We have pi times delta of omega minus pi over 2 plus delta of omega plus pi over 2. I guess we need another one of those. And let's go down a little bit more. I'm going to bring this over here. Now, convolution is distributive, so I'm going to pull this pi out front. So I get 1 over, I'd have pi over 2 pi, and everybody knows what that is. That's equal to 1/2. 1 over 2. And now I'm going to apply the distributive property, so I get x of j omega convolved with delta of omega minus pi over 2 plus x of j omega convolved with delta of omega plus pi over 2. And the sifting property from module 2, I believe it's module 2, that applies right here. The sifting property is just going to be that x of j omega convolved with a delta of omega minus omega naught is equal to, so we'd have 1 over 2. It would be x of j omega minus pi over 2 plus big X of j omega plus pi over 2. If you don't remember the sifting property, go back and look it up. And I'm pretty sure I made a video about it for one of the midterm practice questions. Go back and watch it if you don't understand it. You need to understand that. But you can see here that all we're getting is we're getting a replica of x of j omega centered around negative pi over 2, and a replica of x of j omega centered around pi over 2. Both of those are scaled by an amplitude of 1/2, which is what we have right here. This whole thing. I'm terrible with this pen, sorry. But, yep, so I'll be back for question 4 in a bit. Thanks.